Well, it's nice to see everybody, and thank you so much for having me here. I've never been to CERN before, and it's such a beautiful place, and I've gotten the chance to meet a lot of colleagues that I don't normally interact with and take a extremely aggressive hike yesterday. So today, the title of this talk is completely different than what I had submitted for this program. After listening to all of you for the last few days, I decided to completely throw away. For some reason, I had it in my mind that this was a computer graphics audience. That clearly isn't the case. So I've chosen a different subset of research from our group that I hope is slightly more relevant to your interests. So if you're wondering if this talk is a little bit disorganized and disjointed, that's because it absolutely is. And such is life. Of course, before I start, I do want to make sure that to highlight that, of course, all the work that I'll be telling you about today is really thanks to the fantastic students and postdocs and so on that we have at MIT. I'm extremely lucky and grateful to be working with these folks, and they're the ones that are doing all the interesting stuff. It's just my job to come and do the difficult things like traveling to Marseille and interacting with my colleagues here. So rather than talking about computer graphics, I thought we would do a bit of a 180-degree turn and talk about something completely different and probably more trendy, which is to talk a bit about some problems in machine learning. And I think specifically, these days, we're all caught in the same kind of challenging universe, which is that the really top-performing models in machine learning in tasks like natural language processing, computer vision, are all sort of out of reach to researchers in their labs back at MIT or in France, because we simply don't have the computer power or the data sets needed to train these kinds of models. And so all of us are trying to find our own angle on these new research problems that works around this kind of fundamental issue, which is that we really can't train some of the foundation models or whatever your favorite buzzword is that are really driving the advancements that we see in the discipline. Now, so what I'm going to try and tell you about today are some attempts in our research group to dig into the pre-trained model architectures that are out there and understand some of the structures that are hiding inside of these pre-trained models, and then leverage and edit and navigate those spaces in different ways. So sort of our research that I'll tell you about today is predicated on the idea that we probably don't have the resources to train something completely new, but we do have the resources to maybe work around the edges, change things a bit, and understand the sort of space of interesting ways to perturb a machine learning model rather than start from scratch. Now, of course, many of us are mathematicians in the room, or I'm a pretend mathematician, and I think when we dig around in the machine learning literature, it's easy to get lost. There are all these, if you Google for machine learning architecture, you get all of these bizarre diagrams that, at least to me, really don't make any sense. But of course, over my career and having spent a lot of time with my own graduate students basically translating these diagrams to code to equations, I think what we all kind of come to the realization is that these diagrams are totally useless, and that the reality of all these flowcharts is that they're just a way to avoid writing down pretty simple math in some sense. And I think we can really understand a lot of the top-performing machine learning architectures as just a sequence of matrix multiplies and nonlinearities, and depending on what trendy, useful architecture you have, the sequence kind of changes a little bit. But at least from our perspective today, it'll be good enough to think about it with this sort of vastly oversimplified perspective. Of course, for example, yesterday we heard about very fine-grained differences between ResNets and other architectures, for example. For today's talk, we're going to view that as a bit of an abstraction. Now, inside of these learning architectures, there's sort of two different useful components here. There's what we might call learnable parameters. So those would be like the elements of the matrices that are reshaping our data as it goes from the input space to the output decision in our machine learning model. And then, so that's sort of like the parameters that the machine learning model is trying to learn or to regress. And then on the other hand, another term that I'll use today is to talk about embeddings. And the idea here is that if we take our machine learning architecture and we kind of unroll it as a bunch of different formulas that are applied one after the next to a data point to start from, for example, an image, and then reach all the way to some decision, right? There's clearly this big sequence of computations. If I stop it early, somehow what I've done is taken my input data and reshaped it in some fashion. And I think something that you hear a lot in the sort of mythology of machine learning is that these embeddings are very meaningful, right? And so people talk a lot about how machine learning models, like neural networks, their job in life is to take this sort of raw data and map it to something that's interpretable. Now, the term interpretable here is wildly debatable. I think it depends a lot on the statistical problem you're trying to solve, the regularization you add to your problem, and how much you believe whether there really is interpretability to be had in the neurons of a neural network. But what I think is absolutely true is that as you reshape your input data into farther and farther layers of these machine learning architectures, certainly you're reshaping your space in a way that's convenient for the learning task at hand, and often that's quite distant from the space that you started with. And so this really, as researchers, gives us an interesting opportunity to say, okay, we talk a lot about our data forming some very complicated manifolds, right? This is this sort of high-level picture that we see a lot in the research community. And that manifold is extremely complicated in the embedding space that we began with, right? Like, for example, the space of raw images. But something kind of nice happens as we move farther down into these architectures, which is that these manifolds begin to kind of unfurl, to be embedded in lower dimensions. And maybe we can begin to actually use simpler algorithms that are designed to traverse these curved spaces if we apply them in these later embeddings relative to the complex algorithms that we might need at the beginning. So anyway, this is a very high-level picture of some of the research that we've been thinking about, is that there's this enticing possibility of, even if we just keep a neural network architecture fixed, it gives us a useful mapping from extremely complicated space that we started with, like this raw data, which is noisy, probably isn't equipped with a metric that we think is very meaningful for our problem, into a space where we actually have some hope of realizing this picture that in the research community we've talked about for a very long time. Like, this idea of manifold learning is probably more likely in these embedding spaces than it is in the raw data space. Although obviously there's a lot of questions there, like where are these embeddings coming from, that we're probably not going to answer today. Definitely not for me. So today I'm going to tell you about some research projects that we've had that are working around the edges of this high-level picture. For example, how can we navigate this sort of manifold of data after it's been embedded by a pre-trained neural network? How can we adjust a neural network to be better at certain tasks, even if the neural network itself is already trained and given to us by some giant corporation that we don't want to work with? And then how can we regularize our neural network architectures to behave like these sort of big models when we don't have the resources to train? So I'm going to tell you about 3 extremely disjointed research projects that are kind of in this theme. Again, yesterday I thought I was going to tell you guys about finite element methods. So if you're wondering if these papers look disconnected, it's because they absolutely are. This is my best attempt to glue together some work from our group that I thought might be relevant to this audience. But we'll see how far we get. And whenever you guys are bored, you let me know and we'll switch to the next thing. So the first paper that I thought I would tell you about is some work from my student Chris Scarvelis in collaboration with an intern Okaris and myself. And that's on these models that we call diffusion models, which are really ways of sampling from some data distribution. Or at least that's sort of ostensibly what they're designed to do. Now, in case you're unfamiliar with these diffusion models, I was too. And of course, it's totally bizarre to me as a person whose background is in PDE. Like, diffusion equation doesn't seem all that complicated, and somehow when you read these papers, they seem vastly, the notation is crazy. The entire machine learning community has suddenly become experts in stochastic differential equation, which I had no training in. And so it's kind of interesting to dig through these papers and try to figure out what's real and what's maybe a sheen of mathematics. But I think at the end of the day, you can really understand these kinds of samplers as trying to solve a problem like what I've written on this screen here, which is that I give you some finite data set, so like some xi that I think are sampled from a distribution rho 1. And my job is to draw more samples from that distribution rho 1. Now, as mathematicians, when you look at a statement like this, of course, this is totally meaningless. Like, if I have a finite sample, there's clearly for almost any model a global optimum here, which is to just give me back a random sample from the data set itself, like basically what, bootstrap, I guess you might call that. And the reality is that that model is actually globally optimal for the diffusion model mathematics. Like, if you actually work through the equations, that's really what you should get. So clearly there's more going on than that sort of goofy problem statement we see here. Now, one of the most popular approaches to sampling is this thing called a flow-based generative model, in our attempt to kind of glue together as many buzzwords as possible. And the basic idea here, these diffusion models kind of fall into this category spiritually, is that you start with a sampler from some distribution that you understand, like the Gaussian, and then you come up with some time-varying process like an ODE, which takes samples drawn from the Gaussian and pushes them forward to samples that kind of look like they came from my data distribution, right? And then the magic of these tools is all about how do you train that vector field to be stable and effective and push forward samples. And there's many different ways that we can do that. The classical diffusion model is one. Another one, which is a little bit easier to understand theoretically, is this thing called flow matching, which was proposed about a year ago. And essentially what they do is they prove a very small lemma. This would be very straightforward for most people in this room, I think, which is the following. So I'm given samplers from my two distributions here, like rho naught and rho 1. And my goal, remember, is to come up with a velocity field that pushes forward rho naught to rho 1 in 1 unit of time. And so the way that they do that in this flow matching paper is very simple. You draw a sample from one, a sample from the other, and then you kind of move it along the line from one to the other with constant velocity, and you regress a vector field against that process. So that's sort of what this equation is saying, right? You draw t between 0 and 1, you do some linear interpolation, and then you want your velocity field to kind of match that linear interpolant. And a lemma that you can prove is that so long as the two distributions you're drawing from, like the Gaussian and the data distribution, are the marginals of this joint thing that's drawing pairs, then the velocity field that you get here really does push forward rho naught onto rho 1. It's sort of easy to trust a formula like this and kind of feel like it's okay. The reality is proving that actually is not entirely trivial. And the good news is that this is very amenable to modern machine learning kind of methodologies, right? So you take this unknown vector field VT here, and now when you have this expectation, you replace this with just randomly drawing samples from your data set, from a Gaussian. And then this is basically just a stochastic gradient descent procedure, right? You draw epsilons and x's, you evaluate this v at some point in time and space, which is parameterized with a neural network, and you backpropagate that through the parameters of your model here. So this is sort of one of the state-of-the-art models for certain sampling tasks. I shouldn't say state-of-the-art because that changes every 5 minutes, but it's certainly one of the categories of models that seems to be performing fairly well for this kind of thing. Now, when we look at this, my student Chris asked a totally reasonable question, which is like, at the end of the day, this is a least squares problem. And in fact, it is a linear least squares problem in the unknown vector field V. Right? And so the fact that we parameterize V as a neural network is a little bit crazy, right? I mean, there's a variational calculus exercise that you can do to just write down a formula for V. Like, you don't really need to write an optimization problem whatsoever. You can, if our task really is to solve that optimization problem, I can write down the global optimum of that, right? I mean, it's just least squares. This is just an exercise. Take the first variation here. And what you get, kind of unsurprisingly, is that this velocity field V ends up being some weighted average of your data set, or vectors kind of pointed toward your data set. And so this is a totally reasonable question, and one that I think gets skipped over in this literature a bit, if I'm going to be on my soapbox, which is that there's sort of a completely reasonable baseline here, which is you train these neural networks for flow matching, and at least in low dimension, you could just use the closed form formula and evaluate, like MSE-wise, how well you actually did in that optimization problem. And what you find is, for a lot of these models, the answer is not very well. and that's like totally predictable, and for a lot of different reasons. I mean, for one, the global optimum of this problem just is like a very complicated way to draw samples from your data set. Like we know we don't want. So in some sense, these sampling problems are a bit opposed in the sense that if we reach the global optimum of our problem, we actually get a sampler that is not so good for our task. Notice that is different than the notion of generalization in machine learning. Right? Like in generalization, I can overfit to my data set and still make interesting predictions on data points that are not in my data set. But here, if I overfit to my data set, the sampler is boring. There's just nothing useful about it. So somehow these things are succeeding because they fail at the problem we tried to solve. And why do they fail? Well, there's a lot of different reasons. One is that we don't train them to optimality, right? We're training on extremely large data sets. Another is that we're using these machine learning architectures that don't have the capacity to learn the globally optimal vector field V, right? They typically have some bottleneck inside of them, which is probably not allowing us to just solve that least squares problem. Now, to me, that's a really fundamental question, which is, okay, so what the heck is making these things work? And somehow, if I were an engineer trying to ask this question, what would I do? Well, I would start with the closed form formula. I'd start with the trained thing. I'd try to understand where they're different and maybe bring one closer to the other until they meet. And so my student Chris, to his credit, spent the last 2 years doing exactly that. And his sort of hypothesis is that there's sort of two moving parts that go on in a lot of these machine learning models. One is that you're taking your data and embedding it into some abstract space before you do this diffusion model. For instance, the typical architectures for that velocity field V have some bottleneck inside of them. So that's one part of the learning problem, is how to basically come up with a good embedding of your data. It just happens to be kind of coded in this other vector field regression problem. And then there's a second thing that's kind of interesting, which is something that I forgot. What was I going to say? Oh, oh right. So one of these things is regressing the velocity field, and the other is just, are you actually learning the mechanics of the diffusion equation or not, right? Like even if you had something with perfect capability to represent this solution, you still might not be getting diffusion, or in this case, flow matching. Incidentally, I'm saying them interchangeably. I know that these are slightly different models, but the math is very similar. So he kind of tried to orthogonalize these two things. For example, if I have a really good trained embedding, can I use the closed form diffusion model in that embedding space and get pretty good samples, or vice versa? And what we found is that by starting with the closed form formula and making some relatively small perturbations to it, in a good embedding space, you can get performance that's on par with like state of the art maybe 5 to 8 years ago. Now, sadly, that's not, these fancy image generators now. I think there's a lot of interesting questions, but it's a really interesting research question, I think, to figure out like what is actually making these things work. In other words, why are we using neural networks for this problem? If you want to break this question down a little bit more, of course, there's really two questions hiding inside of it. One is, if you look closely at that closed form formula, there's a sum over your entire data set. So it could be that you're just using it to cache your data points. I think that's probably unlikely as the explanation. And then the other one is that somehow we make more interesting samples, but of course we don't have a good mathematical formulation for what interesting means here. In any event, I think there's a lot of fantastic research questions. Mostly this is just a plea for you guys to help us out here, because we really don't understand what's inside of these generative models. And I think we're quick to write down all kinds of equations because we're good at that in like SDE and diffusion and so on. And they kind of miss the point, because we actually have a solution to the problem that we're analyzing. It's all the ways that we deviate from that problem that I think are really interesting and challenging. And that somehow the engineering folks that are less concerned with us are way ahead of the mathematical community. In any event, so our paper lays out some fun experiments where essentially by sort of perturbing these models in just small ways, like adding Gaussian noise at different points in the formula for the closed form formula for the solution to this problem, you can improve the effects quite a bit. So recall that the optimal velocity field that I told you about before is just some weighted average of data points. If you take those averaging weights and you add Gaussian noise in the right place, then now what you can show is that you can engineer a velocity field that doesn't just point toward the data points, but points towards sort of weighted barycenters of your input data, which sort of feels like the right behavior that you might expect for one of these diffusion models, right? That it's not just sampling from the data set, but kind of averaging nearby images, for example. And that turns out to be enough to get some really nice performance, again, on relatively simplistic tasks compared to what's out there in the engineering side. So for example, here's a two-dimensional thing where we have this checkerboard pattern on the right-hand side. We have this finite data set, blue here. This is kind of like our data set of images. So like we're not sampling from the checkerboard pattern, we're sampling from the blue points. And as we adjust that Gaussian noise parameter around, for admittedly sort of having to noodle with that parameter a bit, you can fill in the space between the data points in a reasonable fashion in a way that sort of begins to anticipate some of the ways that these diffusion models behave. So again, rather than training a giant neural model and sampling from this stuff, solving this variational problem, and then using it to integrate an ODE, all we're doing here is taking the closed form formula for diffusion, adding a little bit of Gaussian noise in the right place, and getting very similar behavior. Yes, Gabriel?
The one is the error, because the issue here is to choose the performance measure. So what is the...
Yeah, that's right.
For classification, we know what is the criteria, but here...
Yeah, that's right. I think it's an open question. For example, in the image generation case, they use this garbage Frichet inception thing, which makes no sense at all. The good news is, specifically for this case, we can, I mean, it's a two-dimensional thing with a closed form. No, but I should, because that would make you much happier with my experiment. No, I think it's in this case we measured like kale or something, but like it's for like a 2D example with a grid of points. I don't think it's a big deal. In high dimension, I think even just measuring performance of these generative models is a really hard task. I think oftentimes people use creativity as a proxy for captures data distribution, and that's clearly the wrong thing to do. That's right, and of course humans are terrible judges of distributional alignment. Oh yeah, I saw this. I think Philippe Isola had this paper recently. Yeah, I'm sure our model would do very poorly by that measure. And again, I think that's the really interesting question. Like at the end of the day, you can do well at the thing that your math problem says you're supposed to be solving. And then you can do well at the sort of high level thing, like generating images that perceptually look good. And those are clearly not the same task. Yeah. If I had to relate back to our broader theme here, so here's some examples that we generated. Again, these are clearly not state-of-the-art image generation diffusion ones. They're pretty good for this celeb A data set that people use for testing sort of face image generation, but clearly it's not, you know, DALL-E or whatever it is that people use today. I think the kind of interesting takeaway here is that by just carefully traversing a well-designed latent space, like in this case, these images are parameterized using an autoencoder. In fact, it was trained using some Jacobian regularization methods I might tell you about later, depending on timing. We can get a sampling strategy that looks promising and is much simpler than training these giant diffusion models. Now, the real research question is, if we want to bridge that gap from these samples, which are pretty good, but clearly not like, you know, penguin on a roller coaster doing, you know, whatever it is that people do in image generation, is that added complexity needed to, you know, to reproduce state of the art going to make this model look just as complicated as everything else that's out there? The answer is probably yes, so still there's a lot of questions to be answered here. But I think the sort of direction of sort of orthogonalizing, like, is the diffusion part of diffusion models actually interesting, or is it just getting a good embedding, is a really good one, and one that I think is worth further study here. Incidentally, I wanted to briefly mention that we just released another piece of research on a different sampling problem involving drawing samples from, so like taking a sample from a distribution and then drawing another sample from the same distribution that's sort of nearby. This is using a completely different set of methodology, but since I know I'm supposed to tell you guys about optimal transport papers, I thought I'd briefly mention that we do have one just this year that's thinking about some similar questions. In any event, returning to our broad theme here, remember the question's all about what can we do to leverage interesting intermediate embeddings that are learned in machine learning models, right? One of the things that we can do, like the previous one, is just kind of traverse that intermediate embedding to make new samplers, right? Like generate new intermediate inputs to the neural network and push them forward through the remaining layers to produce new interesting images. That's sort of what was going on in the previous paper. Another thing that people do these days in this weird apocalypse we're in, where we can't train the big models, is to try and fine-tune them to do different tasks. Like maybe I have ChatGPT, but now I want ChatGPT that talks like a pirate or something like that. And the suspicion is that that should be an easier task than training a model that needs to learn the English language from beginning to end. And so this is this idea of parameter efficient fine-tuning, PEFT is what I'm told. Which I think is really one of the interesting ways where our community, as people with relatively little compute power, have a hope of being able to contribute, because the whole idea here is to be able to make, you know, interesting developments without needing to resort to training this giant thing on a huge data set. Now, if you dig around on like the popular science engineering kind of websites for different models for parameter efficient fine-tuning, there's one that is, I think, used most broadly. It's really funny for me because like these people are in some sense reinventing linear algebra, but of course attaching their own language to this, which is cool. Like I don't think this is a negative. I think it's an interesting community that's like figuring out that like the applied math has something to say here. And in particular, one of the methodologies for parameter efficient fine-tuning that's very popular is something they call LoRA, or low rank adaptation. It's a very simple idea. So I take my pre-trained neural network, so in this case, like W0, remember that's the like generic pile of matrices that goes into my machine learning model. And those matrices are large, right? I mean, there's like billions of parameters in these things. And typically training them on my GPU is very difficult. I need a big data set for that to make sense. So a simple thing that you can do is say, oh, well, if I want to fine tune my model, I'm going to leave the matrices alone, and I'm going to add a low rank update to these matrices and just train the elements of the low rank matrices. So here I've got this BA product, and B is maybe a tall but thin matrix, and A, actually I guess it's transposed here, so it's also tall but thin. But the idea is that there's far fewer parameters in A and B than there are in W0. Does that idea make sense? So like I have some pre-trained model for a generic task. I have a new data set that's much smaller. So what I'm going to do is learn a perturbation to the pre-trained model by just optimizing B and A, and that's a much smaller thing. This is called low rank adaptation, if you're curious. Now, if you read through the documentation for the software for LoRA, there's some really interesting and kind of curious practical advice that like, when our postdoc Jiacheng was beginning to look at this, they all offer you the same thing, which if you read it seems kind of oddly asymmetric, but it's very consistent among the different software packages. In particular, they say, okay, well, when I want to optimize this model, I probably want to initialize it at the pre-trained model, like at the thing that I know works, which means that I need either A or B to be 0 when I start. And the question is, which one? Now, when you read through the documentation, the kind of interesting thing is they all tell you the same thing, which is initialize B to be 0 and A to be Gaussian, which of course is like kind of a strange thing. Like if you could easily do the opposite of that, right? You probably don't want them to both be 0 because then you won't get anywhere in gradient descent. And moreover, there's a lot of other kind of asymmetries that are all in the practical advice you read about this stuff. Like you should use a different learning rate for these two parameters, which also kind of feels weird. Or even in some applications, they tell you to just freeze A entirely and just optimize B. Like in fact, there's some research papers out there that use Gaussian random for the second thing in their product here. And so we set out to try and ask the question of, well, why the heck is this the case? And it turns out that there's actually some really nice linear algebra you can do to explain precisely what's going on here. Now, I think a lot of us were around maybe 10 years ago when it was all the rage to talk about sketching and projection, and the idea that if I have a Gaussian random projection of high-dimensional data into a low-dimensional space, I tend to preserve distances between data points. So in some sense, if you think of that matrix A as like a random projection, it's not entirely surprising that we can get away with randomly projecting onto a low-dimensional space and then just learning sort of the, mapping back from that low-dimensional space to the high-dimensional one as our low-rank update. And indeed, that's roughly what's going on. So for fun, in a paper just a couple months ago, of course, we strip away all the hard parts and just do the easy problem that's tractable first, which is least squares. And it turns out even in least squares, you have the same asymmetry, which is to say that if instead of looking for a matrix in the least squares problem, I look for a low-rank update to a pre-trained matrix in solving linear least squares, then what you'll find is that the closed form formulas for A and B, oops, I forgot a transpose here, are completely different from one another, which is not surprising. You could all do this on scratch paper. And what you'll find is that if you kind of step back 10 feet from those formulas, one of them incorporates the data distribution entirely, like the relationship between the x's and the y's, and the other basically incorporates just the covariance of the x's. So I think this is one way to kind of explain what's going on. In fact, you can prove a lower bound, which says that if I give the option of only training A or B but not both, you can always get a strictly lower cost for linear least squares by just training the outer matrix. In our paper, we also show some kind of nonlinear results. Of course, in that case, it's much harder. I think there's sort of two different ways that you can go. So there's some papers out there that analyze this LoRA model by removing all the nonlinearities. I think we saw some examples of that yesterday, not in LoRA, but that sort of strategy. And indeed, I do think that this would be amenable to that style of analysis. We were trying to explain what happens when there are nonlinearities, and the best you can do is some kind of Taylor series argument, in which case it kind of reduces back to this one here. But in any event, I think there's sort of more fine-grained mathematics to be done here to understand and analyze this asymmetry, which from a practical perspective is very important because it tells you how to actually train these models. So that was about a year ago. My student Rickard, who was working on this with our postdoc, is a more practically oriented guy, and said, well, this parameter efficient fine-tuning model is one way to reduce the size of your learning problem, but nobody's arguing that it's optimal. We don't know that that's the right way to parameterize these updates to neural networks. For all we know, these are extremely nonlinear spaces, right? And in fact, that's almost certainly the case. And I think there's a really fun research problem hiding here. So in particular, if you go on Hugging Face, which is this website where you can download lots of machine learning models, at this point, there's an ecosystem of models around every one of these bases. This is super cool. Like if you want to just spend a time like digging around on the internet, there's some really cool data out there where essentially, for example, let's say there's ChatGPT. There's this odd trend in industry to actually share the weights of your model online. You can just download these things, which means that people then fine-tune them in all kinds of different ways. And so you can assemble a data set of just fine-tuned versions of the same base model. And I think this is fascinating for a few reasons. Now, the base model itself is wildly complicated. There's like billions of parameters. We have no hope of training these things, at least in my lab with this like 3 SAD GPUs we have underneath the desk somewhere. But these data sets of different fine-tuned versions of a model are much smaller, like in the order of hundreds or thousands. And moreover, I think they reveal some really interesting structure, which is what are the different ways that I can perturb a neural network's parameters in a way that is meaningful for different machine learning tasks. Right? Like clearly, if I take a pre-trained model and I just randomly perturb it somehow, I probably won't get an interesting machine learning model back. But at the same time, there's clearly some interesting lower dimensional space, right? That's sort of what this LoRA thing is trying to get after, of different ways that I can update my model that are interesting and are probably not all that high dimensional relative to certainly the size of the neural network and possibly even the size of these LoRA matrices. So as an initial step in this direction, my student Ricard scraped this Hugging Face thing, and for a few different base models was able to assemble data set on the order of like hundreds or thousands of different updates to some of the popular pre-trained models. So you guys should all download this thing and do some cool statistical analysis. It's an odd space to do statistics in for lots of different reasons. For one, so let's say that I have a data set of low rank updates to a machine learning model, like a bunch of different A-B pairs. Of course, it's the product of those matrices that's meaningful. So like PCA on the A's doesn't really make sense. But even more than that, of course, these things are not just cognizant. They're not just matrices, they're matrices that act on different spaces. And like, how do you incorporate the input data space and so on is quite challenging here and something that we're just beginning to think through. So I think there's like lots of fantastic questions hiding here, like how much information really is in a collection of these LoRA updates, or never mind LoRA updates, just updates in general to a base machine learning model. Can we parameterize it in an interesting way, and can we compress that set? So for example, you could imagine a universe where you say, oh, the space of interesting updates to ChatGPT is actually only 20-dimensional, and that's like something I could store on my phone. So I have some hope of like fine-tuning, a base model to be responsive to my, the particular typos I make when I type on my keyboard by just training those sort of high-level parameters that I've extracted from this space, rather than navigating this raw space of neural network activations, which we know is not the right space to work in. In fact, I'll provide you with a little more evidence of that momentarily. So moving in that direction, we actually began to study some different ways that you might compress a set of these updates. The obvious thing that one might do is some kind of SVD. Here, it's a little bit more complicated than that because you have a bunch of different A-B pairs. So like, it's not clear what matrix to do SVD on. So the right tool out there is something called joint diagonalization, which is just SVD applied to a bunch of matrices kind of simultaneously. So we recently kind of shared a paper that gives a nice algorithm for doing that in a way that's sort of tuned for these lower updates, and can take this large collection of already compressed updates, they're low rank, and make it even lower dimensional. Because it turns out, unsurprisingly, that if I take a base model and adjust it for different tasks, they often have a lot in common, right? So you can compress these things even more. I think there's still some interesting things to be done here. It's not clear that like a linear model for compression really makes sense. But I think this is sort of a first step to figure out like what is the interesting nonlinear space of model updates that's actually relevant in this domain. I should also mention this is a spectral problem and it's Halloween, and this was as close as I could get to any relevant joke about ghosts. Okay, unfortunately in the same paper, in addition to proposing these algorithms for joint diagonalization, we also prove a negative result, which is a little bit depressing. It says that if you have a big collection of these LoRA updates and you do joint diagonalization, with high probability you actually will get a very bad approximation rate. And essentially what the statistical question that I have for you guys is to reconcile that with the empirical results that we have. And I think it's more evidence that this is an interesting and weird space to think about. You might notice today I'm just giving you lots of questions and very few answers. In particular, on the one hand, so we proved this result later. We started by doing all the empirical and algorithmic stuff, and it worked really well. So when we derived this theorem, kind of saying, I mean, if you never mind all the words here, you just look at the equation, you hear that this is error, relative error, and notice that it's like 1 minus 1 over n, which is not good. And these two things don't go together all that well, right? On the one hand, necessarily, these low-rank approximations are doing a bad job when you put them in the same basis. On the other hand, empirically, we could compress quite a bit and still get okay performance. In particular, here's a really interesting plot. So on the horizontal axis, we have reconstruction error. So here we take different updated versions of machine learning models, and then we compress them into a much smaller amount of space, and in a lossy fashion. This is not just like a zip file. And then measure performance on the original data sets on which they were trained, right? So you expect it to get worse. Now, initially this plot from like 50 feet away kind of feels okay. Like, yeah, you increase approximation error, the performance goes down, like that makes sense. But if you actually look at the axes, this is kind of shocking to me. We tested it on a number of different models, and just repeatedly, because I didn't really believe this plot. But even with up to 50% approximation error of these low-rank updates, the performance on the data sets that the low-rank updates were trained on really doesn't change. And so what that means is that probably these low-rank updates are not a good way to parameterize in an efficient way updates to a machine learning model, because clearly there's a lot of redundancy. These parameters are not being used in a meaningful fashion. And I think this is a really promising result in the sense that it suggests that there's a lot of structure hiding here and we don't know what it is. And it's not just undergrad linear algebra, sadly for us. So in any event, somehow our compression technique works quite well, but the analysis techniques from just standard linear algebra are kind of failing us here, probably because they're unaware of the data distribution and the nonlinearities that are happening in these networks. But at the same time, from a practical perspective, it's quite beneficial. So for example, here, Rickard actually implemented, to his credit, like an entire server system for testing this thing, where you're simulating this situation where everybody has their own personalized low-rank update that's getting kind of handed back and forth to the server. And of course, by compressing this, you can get much higher throughput, which is what you want. So the plot here is just software engineering, but what it's showing is that there really is some promise here that if you can compress these things even more, it's not just a question of storage, but also efficiency. Like you have some toehold into this universe where everybody has some personalized sort of updated version of a base machine learning model. So anyway, I think the takeaway from this little segment here is that this manifold of interesting model updates is really nonlinear, hard to think about. We don't have a good metric on it. And it's a really interesting space to kind of study in future work. And moreover, even simple linear algebra techniques are useful in this very nonlinear universe for compression and simply understanding that object. Now I know I'm low on time, so I'll just briefly mention one other paper that we had. Oh, we're okay on time. Fabulous, then I'll take my time. In this case, not just on navigating these spaces or even updating them a little bit, but now we had one additional question. This is actually also with my student Chris on, if I have a smaller data set or a noisy data set, can I hope to get a meaningful embedding anyway? This paper is admittedly a little bit less connected to foundation models than the first two, but I thought it's a fun one and actually closely relates to some talks we heard this morning. So I thought I'd share it anyway. Now, what we've seen actually yesterday and today were a few different algorithms for nuclear norm, or rather Jacobian regularization, which I think is a standard technique we've known long before the latest universe of machine learning. So I think a very typical thing to do if you're learning some map into a space is to look at the Jacobian of that map. And of course, if it's scaled very poorly, then that's an indicator that your map is not so good, either because it's not mapping into some thin slice of the target space or simply because it's noisy. And of course, the difference between those two sort of high-level pictures is the difference between having a least squares problem and an L1 problem, right? So in particular, oftentimes we want to parameterize spaces like this S-shaped surface on the left-hand side, right? This is sort of standard test case, which is locally two-dimensional and sort of globally three-dimensional. And so if we want to learn a map into this manifold, we expect that the Jacobian of this map is rank 2, right? Because locally, it looks like a two-dimensional plane. And so oftentimes we're solving machine learning problems and we want to regularize in a fashion that encourages that locally your learned map maps into maybe a lower dimensional space. And I think the sort of standard answer for how to do that is to regularize the Jacobian of the map to be low rank. And one way to do that is to use the nuclear norm, which is the sum of singular values. I think there's probably people in this room that know a lot more about nuclear norm regularization, especially in the context of imaging, than I do. And so essentially, this is penalizing the rank of the Jacobian to have some lower intrinsic dimension of your map. And in particular, we looked at an application which I think is sort of tailor-made to this setting, which is denoising, which we've also seen a little bit of yesterday and today, where my task here is to take a noisy image and map it to a clean one. There's a lot of standard approaches that people do for this. One is that if I have a data set of just clean images, obviously, it's very easy to take a clean image and make it noisy by adding Gaussian to it. And so you can train a neural network that simply tries to reconstruct, right? You have a data set of clean images, you add Gaussian noise to each clean image, and then you penalize the image of your neural network applied to the noisy thing minus the ground truth, right? So this is sort of, I think, a standard technique. There's lots of variations of it out there in the literature. And indeed, it works quite well. The only problem is that it requires having a data set of clean images, which in a lot of applications is not possible. And so one thing that we can do instead is to try to use this Jacobian norm regularization to get around that. Oh, 10 minutes. That's so much time. Fabulous. So in particular, in this paper we propose, I don't want to say we propose because I think there's a lot of folks out there that do similar stuff. A variation of this model, which says that on the one hand, I'd like my map to look somewhat like the identity. Oops, I'm told I should use my mouse to point here. So for example, let's say that I have a data set of only noisy images, and I want to learn the map from that into a data set of clean images. Obviously, this problem is ill-posed, but one way that I might go about it is to say that on the one hand, I expect my map to look like the identity, right? I don't think that, like if I take a noisy image and I put it into my mapping, I expect it to look relatively close to the input. So maybe I even just penalize that with least squares, which is probably what I should have put there instead of L. So just like x minus f of x. But on the other hand, I want my map to kind of take this noisy space and contract it into a lower dimensional manifold. So maybe I say I want, oops, oh no. My mapping on the one hand to look like identity, on the other hand to have some local kind of low rank structure, and nuclear norm regularization gives me one way to do that. The good news of a model like what I'm showing you in yellow here is that it only requires sampling from the noisy data. I didn't need to sample a clean image, right? I'm just saying that like my ansatz here is that a mapping into the manifold of clean images kind of looks like identity, but also kind of has low rank in the Jacobian. So this is an example problem that we can study, but I think it's one of many where you want to normalize the Jacobian of a map to be low rank. I think it's not hard for us to cook up examples of that. And of course, in linear algebra, there have been many different techniques out there for doing this kind of thing. For example, just computing SVD and truncating small eigenvalues is in some sense an analog of this in the linear case. And in that community, there's a really nice lemma that's out there. I was actually unfamiliar with this, but apparently it's a foundational result that was a hole in my linear algebra education, which is that you can compute the nuclear norm of a matrix, which is the sum of its singular values, using a variational problem, really just an optimization problem given on the right, which is that you look at the space of factorizations of A into the product of two matrices, and you optimize the sum of their Frobenius norms squared, and the minimizer of the right-hand side, so long as the rank of UV transpose is at least the rank of A, is actually exactly the nuclear norm. I'm not sure the best intuition for this result. I think one way you can kind of think about it is that U and V are kind of like square roots of A. And so from that sense, it makes sense that the right-hand side is squared and the left-hand side kind of isn't. But it's just like a small exercise to prove this. There's a lot of different ways you can do it. And so what we set out to do was to take this result, which is for matrices, and extend it to the case for these nonlinear problems where we want to regularize Jacobians. Like you could easily apply this result to a linear map, and what you would get is some version of the previous slide. And indeed, you can do that. So we proved a nice theorem. When I say we, I really mean, Chris did all the hard work. I just drew pictures on the board. Where essentially, here's what you do. So you have to kind of think about what the right analog of this linear algebra result is. And the one that we came up with is as follows. So let's say that I have a map F, which goes from my input space all the way to the output. And I factor that as the composition of G and H. So for our case, we chose everything to be infinite differentiable because we're lazy analysts. I'm sure you could do better than that. And we look at all of the different ways you can factor F into this composition. And now what we say is that, let's say that I want to optimize the problem on the left-hand side. Remember, that's this nuclear norm regularized problem we started with. If we want to apply that lemma from the previous slide, which says that I can take matrices and kind of separate them into their two factors, in this case, I'm taking the Jacobian of my map and separating it into the product of the Jacobian of like H times the Jacobian of G. So there's some analog here, right? And so you might conjecture that you can apply sort of a similar reasoning, right? That like somehow the squared Jacobians of G and H added together should give you something that looks like the nuclear norm of Jacobian of F. And indeed, that turns out to be the case. This is not an obvious result. I think it's easy to look at it and feel like it's obvious, but the reality is you can't just apply that lemma on the previous slide pointwise. But it turns out to be true. So like this is sort of a nice nonlinear extension of that previous thing. And from the perspective of machine learning, it's fantastic because machine learning models, what do? Well, they're compositions of a bunch of functions, right, that start with your input space and then have layers and layers and layers. And the lucky thing for us is typically an intermediate layer tends to be very low dimensional relative to the input embedding. And so that's the one where we choose to cut our F into G and H. And so the Jacobians end up being much smaller than the original space. Moreover, we can use some nice randomized kind of estimation techniques for approximating these Jacobians. And what comes out is a really nice nuclear norm regularized formula specifically tailored for these neural network applications that's sort of leveraging the structure of these neural networks to regularize them in an efficient fashion. So kind of to conclude here, we're able to get some nice results for denoising problems. We originally were targeting, kind of unsurprisingly, given that this student is the same guy that was doing diffusion, training those diffusion models. That turns out to be a little bit more subtle. I can tell you about that later. We additionally to that can apply Jacobian regularization to like kind of regularizing the latent space of an autoencoder to be a little bit more meaningful, but maybe I'll omit that because I'm low on time. But essentially the point here is that these tricks of functional analysis are still applicable in this high dimensional space. They just require a little bit of massaging and thinking about to apply the right way. And I'm out of time. But we also had some work on learning proximal operators, which is sort of related to this kind of smoothing idea. But I can share that another day. In any event, I know I'm low on time now, so I'll stop here. But I think the point is that even though we're all in this crazy time when we can't actually train these giant models, there's still a lot of room for us to provide insight, possibly in the ways that we analyze the embeddings of those models and how to change them, rather than just the sort of raw task of training it to begin with. And that there's so many open and cool problems here to be studied that I think are really meaningful and worthwhile, and not just toy problems to study. I guess if I had to put all of these papers together, I attempted to kind of make some kind of schematic here, but I won't even attempt to explain it because the reality is this is a disjointed talk. But it's it's such a pleasure to share this work with you guys over coffee. I hope that I can get all of your feedback and reasons why my math is incorrect. And thank you very much for your time.
Thank you, Justin, for this very nice talk. So, is there any question in the room? Yes,
So at some point you presented some joint diagonalization algorithm.
Yes.
And it made me think about what people were doing for independent component analysis.
It's exactly the same.
Where they did this.
Yep.
So it is the same.
It's very close, sorry. There's some terms that are specific to this problem.
But for instance, do you use an algorithm for ICA to solve your problem, or do you have to use different algorithms?
It's a good question. We couldn't find, so we actually wrote down 2 different algorithms for fun in this paper. They behave about the same. They're totally obvious. Like it's, like freeze one matrix, optimize the other kind of thing. So I would suspect that there's an algorithm out there. The novelty here is less the algorithm and more applying it to this space.
Maybe Rémi is an expert.
What was that?
Maybe you should ask Rémi Gribonval.
That would be fabulous. Yeah. Like we had 2 different ones, one that did that and one that used some fancy dual formula.
And is there some philosophical connection between what you do and independent component analysis, or is it just like
sorry, I didn't.
Is there some philosophical or maybe connection between what you do and what they do in ICA, or is it just that you use the same algorithm but for different purpose?
It's a good question. I don't think about it. I need to know an expert in ICA. I think fundamentally this is it's like a collection of operators that we're
they
compressing.
Use like a fourth order like kurtosis, and they co-diagonalize kurtosis.
My suspicion is that there would be some connection, but like it would take a little bit of work to make it. Yeah. Okay. I don't know. It's a good question. Yeah, I would love you guys' help. I don't know much about ICA.
Any other question? Yes.
I didn't talk enough. I've exposed myself.
Thank you. Thanks for a great talk. I was wondering about this bubble plot you showed in the second section.
Yeah, isn't that weird?
Did I see it correctly that if you reduce your matrices, the error the performance even goes up?
You're saying to this middle point. It's true. So I think what's going on is, which is actually something that's been noted in previous work. This isn't just ours. That there's some duality very roughly between compression and improving on generalization, right? Which sort of makes sense in the sense that if you view generalization as cutting out some overfit part of your model. So indeed, when we jointly diagonalize everything, so now in some sense you're incorporating a tiny bit of other people's data sets into your new compressed version of your learned model. Performance increases ever so slightly, but I would hesitate to claim that it's even statistically significant. But it is true that this is a consistent pattern. The curve goes up a tiny bit and then dips back down.
Thank you.
Yeah. To me, the really noticeable thing is that the point at which it dips back down is 50%. This is a lot of error before things begin to decline.
Thank you.
Incidentally, one small thing that I didn't mention, you could also test one LoRA on a different LoRa's data set just to make sure that it's not the case that you're fine-tuning and it's just the case that you're seeing more data and they're actually all behaving equally the same. And that turns out to not work. So this is the right pattern. Yeah. Okay, I think I'm cutting into the next talk, so I should stop it there.
We have time for one last question.
Shoot.
Yeah, sorry.
I was in such a rush.
This session, the second session is a bit longer than the
Ah,
first one.
yeah, I did my math
I
wrong.
just realized on the program. So, is there any other question in the room? No. Okay, so I have one.
Ah,
No, I missed someone? No? No, I have one. So, about diffusion model. So, the first part of your talk.
yes.
So, I'm not sure I understood everything that you said, but you said basically at some point that the mathematical modeling, we probably don't need all the stochastic differential equation and stuff because if you compute a global optimizer,
Right.
then it's not good.
Yeah, I mean, like that's a controversial claim, right?
So,
Clearly, but yeah.
So what's important, and should we throw away all the modeling?
I think it's a good question. I mean, I think the thing that we have to be cautious about is it's easy to prove theorems about the stuff that we know. And the good news is diffusion models look like SDE, and we're good at proving theorems about SDE, and so maybe we should do that. But the reality is that the SDEs they're solving is pretty simple. It's not like the fancy ones they're using in economics or whatever. I think the right question to ask then would be like, there probably are interesting analytical results from that universe that are relevant here. But it's not so simple as just analyzing the diffusion equation, right? Like it has to do with the interaction between the architecture of your neural network and the SDE. And moreover, like the dynamics of trying to approximate diffusion in a space with a bottleneck might lead to an interesting SDE in the bottleneck space that we don't know anything about, right? I mean, for example, these neural tangent kernel people are one example of a community that's tried to understand how these different function spaces are connected to one another. And that I think those are where the really interesting questions are. Like, clearly these models are doing really well, and it seems to be some combination of architecture, training procedure, and so on. I don't think anybody in the practical side is saying that like, oh, the way to make it better is to better approximate this SDE. So then why are we trying so hard to analyze this particular one is not so clear to me. But that's obviously a controversial claim. It's easy for me to say that with no replacement, you know.
Okay, thank you again, Justin.
Thank you.